So what is important to a bomb? There are three aspects of fissile material that matter to a bomb. The first is the reactivity of that fissile material, which is one measure is the critical mass, the minimum amount required for a chain reaction. The ease of handling, the stuff is incredibly radioactive or incredibly hot. It's rather difficult to deal with, so that does matter, ease of handling. And the neutron background, which is the spontaneous fission rate for the material that you're using, the fissile material. And I'll explain why that matters as we go along. So let's compare reactor grade versus plutonium, weapons grade plutonium. Now, all plutonium is man-made because it has a half-life of 24,000 years. So any that was created in the beginning of the solar system has long since decayed away and disappeared. And you make it in a nuclear reactor from uranium. And there are many isotopes of plutonium, and the length of time that you leave it in the reactor determines the relative abundance of the different isotopes of plutonium. So typical compositions are shown here. Reactor grade has a lot of 240 typically, and less 239, 239 being the good stuff that you like for a nuclear weapon. Whereas weapons grade has 93.5% 239 and only about 6% 240, and the other isotopes are negligible. So you often, if you read definitions of reactor grade, it's often defined as anything with more than 18% plutonium 240. So this explains somewhat how plutonium is generated in a reactor. Down below on the x-axis, you've got fuel exposure in megawatt days per kilogram of fissile material. So think of that as the length of time you leave the fuel in the reactor. And then the composition of plutonium generated is on the vertical axis here. And when you first start the reactor, all of the plutonium that's made is 239. And then that 239 begins to absorb neutrons in the reactor and transmute into 240 to 241 to 242. And so you grow in these other isotopes as you diminish the amount of 239 in the reactor. Okay, so reactivity here. The easiest way to compare fissile materials for a nuclear explosive is to compare the fast neutron or prompt critical mass. And you see here, weapons grade plutonium, the prompt critical mass, the criticality to fast neutrons is 11 kilograms in a bare sphere. Reactor grade is 13 kilograms, barely different. You might not even be able to tell the difference in weight if you held them in your hand. Whereas uranium-233 is 16 kilograms, and highly enriched uranium, which no one would argue isn't usable in a nuclear weapon, is 56 kilograms. So any of these would be better than highly enriched uranium. And the lower the critical mass, the less weapon you need in a weapon, and the less material you need to make a weapon. So there are three ways to cause a fission explosion. You can increase the mass of fissionable material above critical for that element. And this is kind of how the little boy device worked, right? You put two subcritical slugs of uranium together to make a supercritical mass for explosion. And that's because the more atoms that you have along the path of a neutron, it makes it more likely that a neutron is going to hit and fission an atom. So mass matters, more is better. You can use a fissionable material with a higher fission cross-section. So plutonium-239 has a higher cross-section than uranium-235. That's why the critical mass is lower for 239 versus 235. And I'll explain this in a little bit more detail as we go along. And finally, you can compress a subcritical mass of fissionable material to supercriticality. This is what implosion achieves. You push the atoms closer together, and because they're closer together, there's less space between them for neutrons to escape. And so the neutrons are more likely to hit and fission an atom if you implode or compress a subcritical mass to supercriticality. So these cartoons I've drawn, I'm sort of representing atoms as the little blue balls. And clearly, if you don't have enough atoms present, the neutron's not going to hit anything and cause a fission or a chain reaction. But if you can put enough mass together, enough of these atoms, a neutron can't avoid hitting an atom and starting a chain reaction and hitting other atoms with the subsequent neutrons that get produced. So subcritical versus supercritical mass is the idea here. So reactivity, let's continue here. There is a misunderstanding, and I'm being generous here. I don't think it's truly a misunderstanding, but I'll give them the benefit of the doubt in the nuclear electric technical community about the utility of plutonium-240 in nuclear explosives. Plutonium-240 has a negligible fission rate with slow neutrons. And most reactors, power reactors, operate off of slow neutrons. And so in fact, the buildup of plutonium-240 in power reactors slows them down. It reduces the reactivity of the material in the reactors. However, 240 is an excellent fissile material for fast neutrons. And fast neutrons are what drive nuclear explosives. So here we have the critical masses of various plutonium isotopes and uranium-235 for fast neutrons. And you'll notice here that the masses are lower because this is more reactive. 239 is 10 kilograms bare sphere, 240 is 40 kilograms, 241 is 12 kilograms, and U-235 again is 56 kilograms. So they're all better than weapons usable 235. And this sort of explains it in a more technical way. What I've got plotted along the bottom here is the energy of the incident neutron. So down at point 1, we have slow neutrons, or reactor thermal neutrons is what they're called. And at 1.0, I've got fast or bomb thermal neutrons, what goes on in a nuclear explosion. And here we have 239, the blue line, sort of doesn't care particularly. It's a little bit better at fast neutrons than slow neutrons. But notice 240, 242, americium-241, all have almost no reactivity for slow neutrons, but they all are comparable to, and in some cases better than, 239 for fast neutrons. And this is the difference between the way a reactor works and the way a bomb works. So fission cross-section. The problem with fission cross-section is that it's a physics metaphor. Essentially what physicists noticed was that certain elements were more likely to absorb neutrons and fission than other elements or isotopes of fissile materials. And so they said, well, gee, it sort of acts like it's bigger. It looks bigger to the neutron than the other isotopes do. And so they came up with this metaphor of cross-section, meaning the areal size of an atom. And clearly, if something is bigger, it's more likely to block neutrons, to absorb neutrons, than if it's smaller and the spaces between them let the neutrons escape. So cross-section matters. 239 has a much bigger cross-section than uranium-235, as an example.